Hi everyone. So today we are going to talk about the solution chapter, and I am starting with the solubility part first because in this we'll be talking about the Henry law, which is very important. So it's better that we first start with this part itself. Okay, so just give me a second. And yeah. So solubility of a substance. See, solubility means if you are dissolving maybe a solid or maybe a liquid in a liquid, either you are dissolving something solid in a liquid or you're dissolving a liquid in a liquid or maybe you're dissolving a gas in a liquid. So we can talk about the solubility in terms of either of these. So we start with the solubility of a solid in liquid. So this is our first thing which is mentioned in our NCERT book. So I'll be talking to you all from each and every line so that even if you get a question from in between the lines in your exam, so you all will be able to understand it well enough. Okay, so solubility of a substance is the maximum amount that can be dissolved in a specific amount of solvent at a specific temperature. Now see what they're saying. We have a specific temperature. Let's say maybe at 20 degrees Celsius we are talking. So at 20 degrees Celsius, if we are having one glass of water, let's say this is a glass of water, and to this I'm adding the solute. So the maximum amount of solute that I can dissolve in this given liquid at this particular temperature, that is its solubility. Okay, so it depends upon the nature of the solute what you are adding, and it also depend upon the nature of the solvent that you are having. That means it depends on the solvent nature, that is the water. So it also depends on the nature of the water that you are having, and the another thing is your solute that you are adding. So it depends on the nature of solute as well. Okay, so it depends on the nature of solute and solvent as well as a temperature and pressure. That means if we talk about solubility, solubility is dependent on the nature of solute and solvent. So I'm writing SNS. Okay, so nature solubility depends upon the nature of solute in which you are adding and solute what you are adding and on the temperature. Because if you increase the temperature, solubility of a solid and liquid increases. But the same is not true for all the things. Maybe for some of the liquid, when you're increasing the temperature, the liquid will start dissolving in the liquid present already inside the glass more. But if you talk about a gas, if you're increasing the temperature, the gas is not going to dissolve more in the liquid. In fact, the gas which was already dissolved will also start coming out of that liquid. So that's why we cannot always say that by increasing the temperature, the solubility is going to always increase. That will be wrong because it is different for solid, liquid and gases. So that's why we always say it depends what the temperature is. Okay, so it is dependent on the nature of solute that you're adding. It depends on the nature of the solvent that you're having in which you're dissolving the solute, and the temperature and also the pressure. Now see, if I actually tell you now, if you're having a solid and which you're dissolving in a liquid, and there if I talk about pressure, so that will not be that correct because solid doesn't dissolve more on application of a lot of pressure. But if we actually talk about gases, gases dissolve in the water or any other liquid faster when you're giving more of pressure to it. Okay, that's why I'm again indicating that pressure is also one of the factor that decide the solubility. Okay, now these factors like temperature is more relevant when we are talking about more of solid, because if you're increasing the temperature, it's not always like the solubility is going to increase. The same is the case as pressure. It's not like as you're increasing the pressure, always the solubility is going to increase. It's not like that. Like in case of solid, I told you, na? But in case of solid, if you're mixing something in the liquid, pressure is hardly going to any play. But if you're talking about gases, the presence of this pressure is very important there. Okay, so from there we just get to know that solubility is going to be described by the nature of solute, by the nature of solvent, and by the temperature, and also by the pressure. That means these are some of the things which is going to decide that what will be the solubility of any substance. Okay, so I know that's clear to everyone. So now we'll be talking about, like I told you, solubility of a solid in liquid first. So if we talk about this now, see, every solid does not dissolve in a given liquid. Like while sodium chloride and sugar dissolve readily in water, like if we are having NaCl, and we put it in water. I think you all know this, that NaCl will break completely and it will dissolve in the water, right? In the same way, if we are adding sugar to the water, it is also going to be dissolved in the water, right? But if we talk about naphthalene, or if we talk about anthracene, they do not dissolve well in the water. But actually, naphthalene and anthracene, they dissolve readily in benzene. This is what is benzene. So this is a liquid solution. So if you're having a benzene solution, and to this benzene solution, you're now adding anthracene. Let's say you're adding naphthalene. So naphthalene will now dissolve in this benzene solution faster. Earlier, when you were putting naphthalene in water, it was not getting dissolved, right? But here now naphthalene is getting dissolved in the benzene solution. Then now that what is it one thing by which this naphthalene was getting dissolved in benzene, but it was not getting dissolved in this water? See, there is a one thing which is said about the solute and the solvent, that like dissolve like. That means the same type of interaction should be there. Only then you can dissolve the things in there. Okay, that means if I talk about NaCl, NaCl is polar and H2 is again polar. So polar is dissolving something which is again polar. But if we talk about naphthalene, it is not a polar compound, right? So because it is non-polar, it is going to be dissolved in non-polar thing. Okay. Now benzene solution is also non-polar. So I think that must be clear to you all. Okay. Now, it is observed that polar solute dissolve in polar solvent and non-polar solute in non-polar solvent. So in general, a solute dissolve in a solvent if the interaction between them are similar. Okay, so they are only going to dissolve when the interaction are similar. So a solute dissolve in a solvent if the interaction are similar in the two, or we may like dissolve, like as we've already said it. So like will dissolve like I've already told you. You all just don't learn the complete paragraph, just take out the zest out of there, just learn that. Like I've told you, if you're having benzene solution, so benzene solution is a non-polar solution, right? So because benzene is a non-polar solution, then in the benzene solution, you can easily dissolve this anthracene or naphthalene, right? So these both things can be dissolved in this. But if you're having water, water is a polar solvent, right? Because water is a polar solvent, then to water, you can either add NaCl or you can also add sugar. So they will readily get dissolved in it. Okay, so this was the important thing from this paragraph. So next one is, so when a solid solute is added to the solvent, some solute dissolve and its concentration increases in the solution. You all know that if you're having 1 glass of water, and to that I'm adding 1 tablespoon of sugar. So then if I'm stirring it, so the sugar will get dissolved in the water. Okay, so this process is known as dissolution. This is dissolution. So mixing of a solute in solvent, this process is known as dissolution. Okay, so this process is known as dissolution. Some solute particle in solution collide with the solute particle and get separated out of this, and this process is known as crystallization. Now see, what is crystallization? I've told you what is dissolution. Dissolution means when the solute is mixed with the solvent, a solution will be formed, right? So this is dissolution. But if we talk about the crystallization, in crystallization, now see what is going to happen. Let's say you have put something in the water, let's say anthracene, and it is not getting mixed. So now the crystals are getting formed here. Why? Because the particles which are not getting dissolved in the water will be collected at the downside, right? And they will start forming the crystals there. So when the particles collide with each other, because they're not getting mixed with the water, they will start forming the crystals. Okay. So stage is reached when the two processes occur at the same rate. So such a condition, when the number of solute particles going into the solution will be equal to the solute particles separating out of a solution, that is known as a dynamic equilibrium. Now, what is this? Now, see, let me take one more example. Let's say you're having one glass of water, and to this you're adding sugar. Okay, you're adding sugar to this. So let's say I've added 3 tablespoons of sugar to this and it is completely mixed with the water. But now I'm again adding one more tablespoon of the sugar to this. So this time, if the sugar is not getting mixed with the water, that means, actually that the meaning of that thing is that what sugar you're adding more is getting mixed with the water. But all the spaces, which let's say these were the vacant space inside the water. And when you added sugar to this, all these spaces are already filled, right? So when you're adding more sugar to this solution, so maybe that sugar will occupy this position, it will again come back, right? And the new sugar which I've added now will come and take this position, and the older sugar which was there in this gap will again come back. That means now there is an equilibrium set up between the sugar particles and the water particles, that not all the solute will be dissolved in the solution because there is not that much space available, right? So for that, this is a dynamic equilibrium, right? Some particles will get dissolved more and more into the water, and some particle will again come out as a solute outside, right? Okay, so at this stage, the concentration of solute and solution will remain constant under the given condition. That means the stage will remain the same conditions because you have not changed anything. But as soon as you will change the temperature or you will change the pressure, the amount of sugar that would dissolve in water now increase. That means, let's say if you have increased the temperature, so now more sugar can be dissolved in this water. That means that sugar will not be collected like this here now. If you're increasing the temperature, you can dissolve more sugar into this water. That was the reason I was telling you that the solubility depends on not just the nature of solute or the nature of solvent, but also on the temperature and pressure. Okay. Now, similar process is followed when gases are dissolved in liquid solvent. So such a solution in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. Now let's say you increase the temperature and you put more sugar to this. Now I want one more tablespoon of sugar to be dissolved in this water. Now that will again not be possible, right? Because there was a limited space which was available in this liquid, right? But still, if I want to add more sugar to this, it's not possible because now the condition has reached, and that is called as saturation. Every person have a saturation. Like if you're talking to me something, you're saying me something, maybe at one time I will listen to it, maybe 2 times, maybe 3 times, but every person have a limit. I am also going to react back when you will say something bad, right? So that means this is a saturation. As we people have a limit, that we generally say this, that yeah, I'm now saturated with this condition, I cannot bear this person anymore, right? In the same way, here the solution also have a saturation and it cannot bear more sugar inside it. So that is the reason it is now becoming saturated. Okay. Now, an unsaturated solution is the one in which more solute can be dissolved at the same temperature. Because let's say you've increased the temperature, okay? You've increased the temperature and some crystals were there of the sugar, but now they are getting dissolved in the water, okay? Still some spaces are left. Now you can still add one more tablespoon of sugar to this, okay? At the same temperature, but now you're not increasing the temperature. Let's say earlier it was 20, to that you've increased it to 30. After increasing it to 30, more sugar was dissolved. Okay. And you're now keeping this 30-degree temperature constant and you're now trying to put more sugar to this. And if it get dissolved in this, now listen to my words very, very carefully. If you can dissolve that more sugar into that water at this particular temperature, at the same temperature, we will be calling it as an unsaturated solution, because you're adding more of sugar to this, and that is easily getting dissolved in this water, right? So the solution which is dynamic in equilibrium, okay, with undissolved solute in the saturated solution and contain the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. So the concentration of solute which is present inside that liquid, that is its solubility. More the solute dissolved in the liquid, more will be the solubility. Lesser is the solute which is dissolved in the solvent, lesser will be the solubility. Okay. Now we will be talking about the effect of temperature, that how temperature can create a difference. So solubility of a solid, if you're talking about a solid and liquid, it is significantly affected by the temperature. I've already told you that if you're increasing the temperature, the solubility is going to increase. If I'm saying this line, it has no meaning. But if I'm talking about solid, that in case of solid, when you're increasing the temperature, solubility is increasing. Now this is giving the correct information, right? So the solubility of a solid in a liquid is significantly affected by the temperature changes. So consider the equilibrium representation by equation 2.10. So this being dynamic equilibrium must follow the Leach-Atelier principle. That means if I talk about solute plus solvent is giving us equilibrium condition with the solution. So as the solute is getting more dissolved in the solute with the increase of temperature, then it will be dependent on the type of temperature change that is going to take place, and that is governed by the Leach-Atelier principle. Whenever you're talking about dynamic equilibrium, whenever you're talking about a dynamic equilibrium, whenever we talk about the dynamic equilibrium, we have to talk about this Leach-Atelier condition, because wherever there is a dynamic equilibrium, Leach-Atelier is going to come into the play. So in general, we can say that if it is nearly saturated solution, so the dissolution process is endothermic. Because now the dissolution process is endothermic, means it is nearly saturated. Now you cannot add more thing to it, right? But if it is not a saturated solution, if you're dissolving more solute in the solvent, it will be exothermic. Okay, so that means if del H is positive, and one condition is del H is negative. Okay, when del H is positive, that means it is endothermic. So the dissolution process, see, exo means when the heat is going out. Exo means heat is going out. And if, let's say, I'm having money in my pocket and somebody is asking for that money, I have to give that money out of my pocket. So will I feel good for that? No, right? So exothermic means when the temperature will be negative. But endo means, let's say, if somebody else is giving me the money and I have to now put it in my pocket, so I'll be very happy for that, right? So that is endothermic. Endothermic means positive. So when the del H value is positive, that means we are talking about the endothermic process, right? And when the delta H is negative, that means it is an exothermic process. That means the solubility should increase with the rise in temperature, and if it is exothermic, the solubility should decrease. So if, let's say, if we are doing, let's say dissolution is there, okay? So dissolution can be exo or endo depending upon if it is a saturated solution or a non-saturated solution, right? Now, effect of pressure. Pressure do not have any significant effect on the solubility of solid and liquid. I told you this earlier also, that if we talk about a solid dissolved in a liquid, temperature plays a very vital role. But if we talk about pressure hardly contribute to this, because the main reason, okay, one question, like if I give you one question from there, one question could be that, okay, why pressure is not creating much difference in solubility. insolubility of solid in liquid. Because see, if you want to clear all your basics, you have to read each and everything, and you have to see that from where the questions can be asked to make your, not just according to the boards, but yes, definitely according to your knowledge as well. Okay. So the reason for this is because if we talk about liquid, I'm answering this question. Okay. Because if we talk about liquid and if we talk about solid, you all already know that solid and liquid, they are highly incompressible, right? They are highly incompressible because they are highly incompressible. So if you're even pressurizing something, if you're having solid and you're having liquid and you're pressurizing it so that that solid get dissolved faster in the liquid, that is hardly going to do any good to that, because solids and liquid, they both are highly incompressible. So that is the main reason why pressure in case of solid being dissolved in liquid is not going to do a much difference. But yes, definitely temperature is going to create difference. Okay. And now the important part is, this is a very important topic from this chapter. And that is the reason why I have taken this topic first. Now, many gases dissolve in liquid. You all know that because of the dissolution of oxygen gas, and not just the oxygen gas, many gases in the water, the aquatic life is possible, because aquatic life, if we talk about fishes, like we people require oxygen, so do the aquatic fishes require, right? So these fishes and all the creatures which live in the water take the dissolved oxygen from the water, because the gas, like you know that O2 is a gas, so it is dissolved in the water, and this is dissolved in the water because of the atmospheric pressure which is around us. Okay, so oxygen dissolved only to a smaller extent in the water. It is this dissolved oxygen which sustains all aquatic lives. On the other hand, hydrogen chloride, you know what, HCl is very it's superbly dissolvable in water. Okay, so hydrochloric acid is highly soluble in water. So solubility of a gas in liquid is generally affected by the pressure and temperature as well, and also depends upon the nature of the gas that you take. Okay, let's first talk about the solubility of a gas increases, like I was already telling you, pressure. So the solubility of a gas increases with increase of pressure. How? Let's see. Let me take two beakers. Let's say this is the first beaker and this is the second beaker. Okay. And to this, let's say this complete is water. And again, this is water. Okay. And let me take a different color. Let's say these are some gas particles. And now these are the gas particles. Okay. Now, see one thing. Let's say here is a piston. You all know what a piston is, right? Now, in both the diagrams, you all can see, okay, I'll label them as figure 1 and figure 2. So if we see the figure 1, because there is not a very high pressure, because the piston is at the top, so the piston is not pressurizing the gas to move inside the liquid, right? The water, inside the water. Let's say these are, let's take them as oxygen and this as the water. Okay, so if this is a gas which is oxygen gas and the piston is at the top, that means not very much pressure is there on the gas to get dissolved, but as you're increasing the pressure, all these gas particles are coming closer to each other, and as they're coming closer to each other, they will be dissolved in the water also in a bigger amount. And this is the reason in the Coke bottles also, you might have seen when you open the Coke bottle, it opened with a fizz sound, because in the bottle also, if you talk about the bottle also, there is a liquid in this, Coke is there, and some gas is there on the top, and not just at the top, in the liquid also. In the liquid also, some gas is dissolved. This gas is dissolved in this liquid. Okay. And you know what? This Coke bottle is closed at a very higher pressure. So if you close this Coke bottle at a high pressure, that means we are pressurizing this gas from the top side. We are pressurizing this gas from the top side to get dissolved in the liquid. But as you're opening the Coke bottle, what you're doing is you're opening the top of it. That means you're allowing the gas which is present there into the liquid and also inside the container to escape out. So as you open it, a fizz sound comes because all the dissolved gases are started to leaking out. And when all the gases are leaked out, now trust me, it smells very, not smell, it tastes very bad, because the actual taste was because of the gas also, and then the liquid also, because all the gases are now passed out, the taste will not be that good. That's why we generally say, and our parents generally say, if you have taken a sip out of it, just close it quickly. Okay. So now let's move further with this topic. So now see, the solubility of a gas increases with increase of pressure. So for solubility of a gas in a solvent, consider a system as shown in this figure 2.1. The lower part of this, okay, I'll show you this and then I'll explain. Now see in this. This is the container 1. Let's say this is figure A and this is figure B. So if we see figure 1, this is the liquid part, right? This is the liquid part, and these are the gas particles, right? So see, when you put only one weight over this, so a little weight is there, and because of that, some particles are dissolved in the liquid as well. But if you're pressurizing it more, when you're putting more weight over this, more gases are getting dissolved in this, right? So effective pressure on the solubility of gas can be easily seen by this. The concentration of dissolved gas is proportional to the pressure of the gas. That means if we talk about that, how much gas will be dissolved in this liquid depends upon how much pressure you are applying. So pressure is directly proportional to the amount of gas dissolved, right? Amount of gas dissolved in the liquid. You know who was a scientist who first talked about this? Henry. So Henry was the first scientist who talked about this dissolution of gas inside the liquid by the application of pressure. That it is a quantitative relation, because if you're increasing the, because we are talking about the quantities here. If you're increasing the quantity of pressure that you're applying, the gas quantity present inside the liquid will also be increased. Okay, so that's the reason in your NCERT book we studied it as the Henry's law, because Henry was the first scientist who talked about this law. And you know, one more scientist was there, Dalton. And Dalton was a contemporary of this Henry. Contemporary means at the same time, Dalton was also of the same age group, you can say, was doing the research on many things. So Dalton said that he was separately doing the research. It's not like they both were doing it together, but they both were doing it separately. So Dalton at that time said that the partial pressure of the gas above the liquid is directly proportional to the concentration of gas present inside the liquid. This is what I'm saying. Partial pressure of the gas. That means the more you will increase the pressure on the gas particles, more the gas particles will have concentration inside the liquid. Okay. So if I open this expression will become like this. And this proportionality sign is changed by this K sign, which is Henry's constant. This is Henry's constant, and P is the partial pressure here. P is the partial pressure and X is the concentration. Okay, and concentration, I'm writing it in terms of mole fraction. Okay, you all know what mole fraction is, that how many moles, like in a complete water, how many moles of the gases are present, right? And you know that if I talk about the mole fraction of, let's say, N of A plus N of B, let's say this is the solvent and this is the solute. Okay, so they complete are going to give 1, because I'm talking about mole fraction. Fraction means you're having something 1 and you're then breaking it, right? So this complete will have 1. But if we talk about the fraction of the liquid and the fraction of this solute particles present in, this can be represented as Na because of solute and Nb because of the solvent. So that's why the Henry's law was P is equals to Kh of X, where this is representing the mole fraction. Okay, I'll be explaining you this in more details. I hope that much is clear to everyone. Now, see, Henry was the first to give a quantitative relation between the pressure and the solubility of a gas in a solvent which is known as Henry's law. So this law states that at a constant temperature, see, I have only written this. I'm not talking about the temperature. So that means we are studying this law, or we are studying this equation at constant temperature. That means if you want to compare the two gases, that how much they are dissolved in, let's say we are having one beaker in which we have dissolved the oxygen gas. Okay. In the another beaker, we are dissolving the nitrogen gas. So if you want to talk about the dissolution of this oxygen gas in the beaker and the dissolution of this nitrogen gas in the beaker, that means you have to, for both of them, the temperature should be constant, because if you are, let's say you're talking about this oxygen gas dissolved in the water at, let's say 30 degrees Celsius, you're talking about this one at 40 degrees Celsius. Then it's very, very obvious that nitrogen will be lesser present in the water because you have increased the temperature. Because of increased temperature, lesser number of gas particles will be there inside the water, because some of the gas particles will escape out, right? That's right. So at constant temperature, we always study this. So what is Henry saying? The solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or the solution that you are taking, right? Now, as I've told you, Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in a liquid solution is a function of, see what he is saying, that the dissolution of a gas in a liquid is a function of partial pressure of the gas. If we use the mole fraction of gas in the solution as a measure of its solubility, solubility is what? How much concentration is there of gas inside the liquid? So he is talking about the solubility in terms of mole fraction. And that's why we are writing it like this. So then it can be said that the mole fraction of a gas in the solution, mole fraction of what? Of the gases, right? Because we are only concerned about the moles of gas. So the mole fraction of gas that is present inside that liquid at that one particular pressure is going to tell us about the solubility of that gas, right? The most commonly used form of Henry law states that the partial pressure of a gas in the vapor phase B is proportional to the mole fraction of gas X in the solution. This is the equation what we write. And now see what is KH here. KH is Henry's law constants, as I've already told you. So if we draw a graph between the partial pressure of the gas versus the mole fraction of the gas. So you're taking the mole fraction of the gas, that means we are talking about the mole fraction, and the partial pressure, that is P. So we will be plotting a graph between the partial pressure and the mole fraction. Now see what is happening. As you're increasing the pressure, now see, we're moving here also. So as you're increasing the pressure, as you're moving to 500 to 1000 and above that, so as we are increasing the pressure, so with the increase of pressure, you all can easily see the mole fraction of gas that is dissolved inside one particular liquid is also slowly it is increasing. Okay, I hope this graph is clear to everyone, because this is depicting the same thing which I have written in the form of equation. And now, one very important thing there is, let's say if I say to you all that this is for oxygen and this is for nitrogen gas. Okay. Now I'm saying that pressure on both of them is same. Okay. And mole fraction, because I'm applying the same pressure on them, then the dissolution of oxygen gas inside the water or the dissolution of nitrogen gas in the water should be same. But it is not the same. Why? Because the KH value, because this KH value is different for different gases. Okay, the KH value is different for different things. So it's obvious from the equation that higher the value of KH at a given pressure, the lower is the solubility of a gas in the liquid. I'll tell you what it is. First, I think that this is clear to everyone, right? Now let me explain more. Now see, what these lines are saying to us is higher the value of KH, because the equation is this. This is what the equation is. X of, let's say, oxygen. So if pressure I'm applying same, the higher the value of KH, pressure, higher will be the value of KH at a given pressure I am keeping same. So higher the value of KH at a given pressure, lower is the solubility of a gas. Why? See, if I'm saying this is constant, let's say I want to keep it as 2, and you're increasing this. I don't want my answer to be changed. My pressure should be the same. If I want this pressure to be the same and I'm increasing my KH value, it is very, very obvious that now my mole fraction value will have to decrease, only then my this term will remain constant. That means if you're keeping the pressure constant and if your KH value is higher, your concentration of your gas particle, that is a solute inside the solvent, is going to decrease. Okay. So it can be seen from this table 2.2 that KH value for both N2 and O2 is increasing with increase of temperature. That means if we talk about N2, okay, I'll write for N2 also. Now, see, with increase of temperature, they are saying that if we are increasing the temperature, now this was seen, when we increase the temperature, the KH value of oxygen also increased, and the KH value, that is a Henry law constant value of nitrogen, was also increased. So that means if the KH value is increased and I'm calling it to be constant and I want this also to be constant, this is increasing, then that means my this concentration value will decrease. This concentration value will decrease, and that is the reason we say that with increase of temperature, the concentration of solute particles or the gaseous particle inside the solution or inside the liquid is decreasing. Is it clear to everyone? Or I can directly say whenever you're increasing this KH value, the solubility is decreasing when you're increasing the temperature. Because when you're increasing the temperature at constant pressure, the KH value is increasing. And because of that, as I've already said, the pressure should be constant. To keep this pressure constant, because this is now increasing, this has to decrease, right? I hope that's clear to everyone. And still, if you people find any kind of doubt, you all can write your doubts there in the chat box and in the comments. I will surely see them and I will reply back to you. Okay. Now, see, I was talking about this. As I'm increasing the temperature from 76 to 88 of nitrogen gas, this temperature is increasing. So with the increase of temperature, can you see the KH value is also increased from 76 to 88, right? Temperature is increased from 293 to 303. The KH value is also increased. That means with the increase of KH value, the concentration of solute has decreased now. Okay. And for oxygen also, see, the temperature has increased, the KH value has increased. Now, because the KH value has increased and I want to keep my pressure constant, let's say at 2. If this has increased, it's very, very obvious that now this concentration of the oxygen gas inside the solvent will decrease, right? Now, see, this is very, very important now. Now, I think I've explained this part very clearly that it is due to this reason that the aquatic species are more comfortable in cold water rather than in warm water. I think now you all can easily understand this, that why the fishes are more comfortable in the cold water but not in hot water. Because when the temperature is cool, when the water is cool, then more gases, more oxygen gas is dissolved inside the liquid, right? But if the temperature is higher, the gases which are dissolved inside the water will be less. And that's the actual reason behind this. That means, see, we are talking about the water, we are talking about the fishes, we are talking about the aquatic life, aquatic species, and there also our Henry law is applied, right? That means science is everywhere and we should be very, very good in our studies, or we should be very we should be very good in observing the things, and we should then apply our concept of chemistry or maybe physics to those natural phenomena, whatever is happening there, right? So I hope that's clear to everyone. Now, we will be talking about more application related to the Henry law, because application is something which you all should be aware of. So just give me a second. Yeah. So questions we'll be doing in one book. All the in-text question and all the NCERT question will be doing in one book. Now see, Henry law finds several application in industries and explains some biological phenomena also. Some of the very notable among the industrial and biological phenomena are these, which we are now going to discuss. The first one is to increase the solubility of carbon dioxide gas in the soft drink and the soda water. The bottle is sealed under high pressure. If you remember, I've just told you all that if you want your soda bottles or your cold drink to be good in taste, what we do, we just put the carbon dioxide inside them, and we pack them at a very higher pressure. We seal them at a very higher pressure, and because of that higher pressure, the carbon dioxide gas which you have added on the top of that liquid present inside the bottle will be now mixed with this liquid, and that is how it is giving a good taste. And because of this, dissolved with water, this acid is also formed, and this is known as the carbonic acid. Okay, I hope that's clear. Now we'll be talking about the scuba divers. Now, scuba divers, you all know that when we, okay, I'll tell you first one thing. This is the ground level. Okay, this is ground level. Now, when you're increasing above, when you're moving up to the ground level, and when you're moving down to the ground level, the pressure changes. So you all know that in the maths, we always draw the graph like this. Here, the positive number increases, and here, the negative number increases, right? So just do the opposite of this. Just put a negative sign on the top and positive sign here. That means when you're moving at the top, that means when you're moving up the hills, when you're going above the ground level, the pressure is going to decrease. The pressure is going to decrease. And when you're going down the ground level, okay, there the pressure is going to increase. Okay. So now when we are inside the water, we are inside the swimming pool, and when the scuba divers, they don't go just like the swimming pool 7 or 8 feet down. They go more than that, right? So scuba divers, when they go deep inside this water, the pressure is increasing. So because of the increase of the pressure, you all know that the concentration, the mole fraction of the gases dissolved inside this water is also increasing. So that means as you're going more and more down inside the water, as you're diving deeper inside the water, the gases which are dissolved in the water are more. So when you're breathing in, you're breathing more of oxygen, you're breathing more of nitrogen gas, and after, let's say you were here. So after doing the dive, when you're coming back at the top at a very faster speed, so suddenly the pressure is now decreasing. So if the pressure is now decreasing, now if the pressure is decreasing, the solubility of the gas is again going to decrease, and suddenly all the gases which are present inside your body, inside your capillaries, so that all those gases want to quickly move out, and because of that, we faces bends, and the scuba divers also faces this bend because of the serious problem. So scuba divers must cope with the higher concentration of dissolved gas while breathing air to a higher pressure. And you know that when you're moving down, the pressure is high underwater. Increased pressure increases the solubility of atmospheric gases inside the blood. So when the divers come toward the surface, the pressure gradually decreases. That means when the diver is coming back to the top side, the pressure is again decreasing. This releases the dissolved gases and lead to the formation of bubbles of nitrogen in the blood. Because all the gases want to come out, they want to quickly move out of your body, but still your blood vessels are not giving that much space. So bubbles will be formed inside your blood capillaries of this nitrogen gas. Okay. And it is a serious problem, and this condition is called as bends, which is very painful, and it is very, very dangerous to life as well. So I hope this application is also clear to you all. We have discussed about 2 applications of the Henry law. Henry law is that pressure, partial pressure is directly proportional to the mole fraction of the gas that is dissolved inside the solvent, right? So based on that, we have discussed two applications, and now we will be discussing one more application to this. Now, to avoid bends, what can be done? We'll be first talking about this. So, as well as a toxic effect of higher concentration of nitrogen in the blood is there. You all know that. So, what we generally do is we take a tank when we're diving in with a little amount of helium in it and nitrogen and oxygen. You know that they are necessary, they will be there, but still helium gas is added there in more amount. Now, at higher altitude, now we're talking about moving up the hill, right? You're moving upside, let's say in a hill. On a hill, we're moving up. So when we're moving on the top side, the pressure is going to decrease, right? So at a higher altitude, the pressure of the oxygen gas is less than that at the ground level. So this lead to the lower concentration of oxygen in the blood. So when we're, let's say, moving up a hill, so when we're going up, because the pressure is less, and if the pressure is less, the dissolved oxygen inside this liquid, or you can say in our atmosphere, the pressure was more. That was the reason the oxygen was not escaping out of the earth, but it was still there on the earth, right? So when you're descending, when you're moving up the hill, so when you're moving up the hill, the pressure is decreasing. Because of the decreased pressure, lesser oxygen is available there, and that is creating, or that will create unconsciousness in our body, because our blood and our tissues or cells are not getting appropriate amount of oxygen that is required, right? So at the higher altitude, the climber face this type of problem, and they have this condition called as anoxia because of this, right? If we talk about temperature, I've already told you all that the solubility of gas is obviously going to decrease with the increase of temperature, right? So when dissolved, so the gas molecule are present in the liquid phase, and the process of dissolution can be considered similar to condensation, and the heat is evolved in this process. Evolved means moves out, right? So we have learned in the last session that dissolution process involved dynamic equilibrium. If you remember, dissolution, I told you, when you're mixing sugar with the water and you're stirring it, this is dissolution. And when you're mixing sugar to the water and you're mixing it, some amount of heat is released. So always remember, dissolution is an exothermic process, right? So you all know that dissolution is a dynamic equilibrium. So again, Lee Chetler is obviously going to come there. And as dissolution is an exothermic process, the solubility should decrease with increase in temperature. So if already, you know that if I'm mixing the sugar and I'm stirring it, already the heat is coming out. So if you're giving it more temperature, if you're increasing more temperature to that, then the dissolution will be very less, right? If we talk about gases, if you're talking about gas, in a liquid, let's say, let's not take an example of sugar and water now. Let's take this as water and gas is there, right? So when you're mixing gas with the water by application of pressure, it will dissolve faster. And you know that dissolution process is exothermic. So if it is exothermic and you're still giving it more, it's very, very obvious it is not going to get dissolved, okay? It is going to decrease. So that means temperature is going to have an opposite effect on it as we wanted. So I think Henry law must be clear to you all. And now this is it for today. We will be now extending this topic. We will be in the next class talking about the limitations of the Henry law. And then our Henry law will be completed. And then we will be moving to some another part. Maybe first we will be talking about the concentration terms, because we will be requiring them all in our next classes as well. Okay. So I hope you all must have got it. And still, if you find any kind of problem with this, you all can post your questions down there in the chat box and I will reply back as soon as possible. And yeah, we'll be meeting in the next lecture. Till then, take care. Bye-bye, all of you.